Good morning, physics students, and welcome to another episode of Physics. It's Mr. Finn coming at you from neighborly Northville. Hope everybody's having a great morning. A couple of announcements today. Let's see here. Tomorrow, I'm going to give you guys the review video by Crash Course Physics. So I will not be on with you tomorrow. Simply just going to review electric fields with Crash Course Physics, maybe voltage, if I can find a good one there. Then we will be taking our quiz, our weekly quiz, or weekly Google form on electric fields, electric potential energy, and the definition of voltage. So those three things: voltage, electric field, and electric potential energy. That will be for Friday. Okay, today I'm going to go through capacitance again real quick. I'm going to introduce two extra pieces to the capacitor puzzle. I will have the capacitor lab ready for you next week, at the beginning of the week, if I can't get it up loaded by tomorrow, but it'll be up definitely by the beginning of the following week. Okay, let's see, what else? There is no final exam in this class for either juniors or seniors. We're just taking it out to the end of the year, same way every week. We'll have a lab, we'll have a little small questionnaire, and then we'll have our Google form at the end of the week. So really, as long as you're getting the videos and you're participating in either the Google Meets or you're getting those questions and Google Forms answered, you should be fine. Okay? Remember last time we left off with a question about the bird. Why is the bird able to sit on the wire without being electrocuted? And remember, I mentioned that a few people erroneously think that birds only sit on the non-hot wire or the neutral wire of the overhead power lines. That is not true. Let's take a look and see what is exactly the problem or the explanation with the bird and the wire. Okay guys, just got a couple things here. Let's look at this bird. Now I drew the belly of the bird and his two legs. I drew a rather big bird here. So I have two lines. I have the hot wire here and the neutral wire here. Now we're going to learn in a few weeks that current is actually the flow of charge through a conductor, number of coulombs per second. So you can think of it as Q, or you can think of it as I, the flow of current. Now, why would the current not damage the bird? It's not that the bird has any unusual characteristics, but remember from last week, we did learn that charge flows from high potential to low potential. So if I had a balloon here with 15 coulombs of charge, or 15 nanocoulombs of charge, and an object here of no charge, the balloon would attract to that neutral item. Charge would be a force of attraction. But this is not the case. How much electric potential does the right foot of the birds have? I don't know. Let's call it 10 volts. 10 volts between this wire and this bird's feet. That's the right foot. What about the left foot? Well, it's the same voltage because the wire is going to have a certain amount of charge, but the bird's feet have zero charge. So as long as the bird is not touching the ground or touching the other wire at the time that he's touching the hot wire, there is no potential difference across the bird's feet. There's simply no way for charge to move up this leg through his heart, killing him instantly, and then down on the other leg again. It doesn't make sense. Why would charge do that? Charge doesn't do that. Charge moves the path of least resistance the best. In other words, charge is going to go along this nice conductor and barely even have any effect on the bird whatsoever. So why do birds sit on the wire? Well, remember, this is the high voltage wire, and so it does warm up. So maybe the birds are just there to warm up their little talons. It's kind of interesting. Anyway, a lot of kids bring all kinds of stuff to the table there, guys. I'm sure you guys had some thoughts about it, like, oh, those wires are insulated. Cross-country wires are not insulated. That would take too much cost. So the bird sits on the wire because There is no potential difference between its feet, and voltage simply does not change between its feet, and therefore charge does not flow. Okay guys, let's look at our capacitors plates again from last time. I mentioned we would do a little bit with this. We have a positive plate and a negative plate. Now what I'm going to say is, just for arbitrary purposes, we're going to put this negative plate at 0 volts. It's obviously not, it's got some charge, but we can arbitrarily determine anything as a 0 potential. Let's put 10 volts up here, where the positive plate is. Now if it's just air between those plates, and we keep depositing charge on those plates, if we keep increasing the voltage and more charge is deposited on those plates, eventually we will get to a point where charge will disperse. Electrons will actually jettison from one plate to the other. And we mentioned that that would be a violation of the function of the capacitor. It would ruin the capacitor. So what is in between those plates? Well, right now we have either a vacuum or air. And air has a certain insulative value. What kind of value, you might ask? Air doesn't ionize until 30,000 volts per centimeter. So if you were to exceed 30,000 volts for every 1 centimeter of air, air would cease to become an insulator and would become a conductor, and charge would disperse. That's kind of like what happens when a lightning blast goes through the air. There's a certain amount of distance between the charged cloud and the ground, and then boom, charged blast goes, because that air has ionized. Now, we give air a certain value, a certain insulative value called K. So remember one of our two formulas for capacitance. We had capacitance is equal to epsilon naught A over D. That holds for any parallel plate capacitor. Well, there's no K in there because it's assumed to be 1. But what if we put a K in there? Simply would get multiplied out front. So our new formula with a dielectric insulator would be capacitance equals K times epsilon naught A over D. Well, the A over D relationship still exists. See yesterday's video for more details. But this insulated material can have a K value much bigger than that of air. And if it's much bigger than air, that means more charge could be stored on these plates without discharging the capacitor. So, by using a dielectric constant, something bigger than air, an insulated value bigger than air, we actually get more capacitance that can be stored between these plates, more capacitant value. So, meaning, if I had a bigger voltage supply, I could push more charge onto those plates. Well, there's actually a chart on this in your book, so if you guys get a chance to work some of those homework problems, don't be freaked out. K, if there's no K there, it's understood to be the number 1. But if there is a dielectric constant, such as some big insulated material like mylar, well, that would be something that we could put in between those plates to separate the plates, number 1, but also stop them from discharging, so that we can roll them up and put them in a cylinder. That's it, guys. Dielectric material is insulated material. Now, wouldn't be the same if it was a conductor. If you used a conductor in between there, you might actually discharge those plates a little bit quicker than you would if it were air. So we wouldn't want to do that. We would want to put an insulator in between those plates. Okay, guys, let's look at one other thing in terms of capacitors. Okay, guys, one more look at something today. I want to talk about the energy stored in a capacitor. We know we've got these plates charged up, and we know there's an electric field between those plates. But how much energy can we actually store in a capacitor system? Well, it's a function of voltage and the capacitor itself. We know that electric field is force per charge. We also know that voltage can be expressed as E times D. And we know our general formula for charge in terms of capacitance is C times D. In other words, a capacitor is a charge per volt, a number of coulombs per volt. So one of the ways that we express this is potential energy, electric potential energy stored in a capacitor, given the symbol U. Now why not E? Because we're using E for electric field. So U is a universal symbol for potential energy. 1/2 CV squared. It looks kind of familiar. It almost looks like 1/2 MV squared for kinetic energy. And that's not by accident. Let's talk about this though. If we want to substitute something, like let's say from this equation, let's say we want to substitute Q equals CV in for C. So the energy of the capacitor could also be 1/2 Q divided by V times V squared, simply by plugging in the definition of capacitor. So one other way of expressing the energy of capacitor, this voltage cancels with this one, and you're simply left with 1/2 QV. So 1/2 QV or 1/2 CV squared. And those units will always come out to be joules. Why is it joules? Because remember, charge is in coulombs, and voltage is a ratio of energy per coulomb. So joule per coulombs times coulombs is going to give you simply joules. That's pretty basic, guys. I'm not going to go into the derivation of this one, but suffice to say that there's two pretty quick ways that you could get the energy stored in a capacitor. And you might have a few homework problems on that. So let's get a look at that before we get going. And we'll wrap up here for today. Okay, guys, so just kind of a short one today. Remember, I'll be on the Google Meet today at around 11. So if you got any questions regarding homework or any kind of stuff like that, conceptual stuff, I can handle them today. And remember, tomorrow you got the big Google form on electric field, voltage, and electric potential energy. And don't worry about capacitors. We're probably going to float those to the other week. Okay, guys? All right, well, I hope you have a great day. I'll see you at the Google Meet. And then tomorrow, your video is by Crash Course Physics on electric fields. And then, of course, you'll have the Google form. So really, I'll see you on Monday after I talk with you at the Google Meet today. Have a great day, guys. Have a great weekend.